Hi everyone, I'm Hao from NUS. I'm glad to introduce our work here. It's about video modeling. We propose a video-oriented chain of thought reasoning framework. And to our best knowledge, this is the very first attempt that successfully implements the COT idea for achieving human-level video reasoning. Let me tell you the whole story. So, accurately interpreting video data is one of the most important goals in the AI community. There has been extensive exploration into building models for video action and dynamic recognition, but right now they might largely suffer from a type of straightforward perceptual level understanding, like for those simple video. We may want to handle the complex videos, which, however, is much more challenging. So think about it, how we humans achieve the deeper understanding for videos. I think there are at least three aspects. First, for achieving precise content perception, a fine-grained perceptual pixel understanding of the video movements is necessary. Most existing video understanding approach focus on instance or patch level analysis, which lacks the precision for accurate object-level recognition or tracking, let alone in-depth video comprehension. Second, profound reasoning demands cognitive capabilities to allow a reasonable explanation and even causal imagination. This often needs common sense knowledge to link the video pixels to the factual world. For example, understanding that jumping from heights can cause fractures, or colliding with the tanker trunk can cause an explosion. Most importantly, for humans, video reasoning is not an instantaneous process, but follows a multi-hop procedures from lower level to higher level. This often involves first identifying specific targets, like red oil tank in these video frames, like see the figure 1 here, then tracking and analyzing its temporal behaviors and interactions with the environment to deduce the scene semantics. And finally, integrating factual common sense to formulate a cognitively coherent response. This motivates us to propose a video reasoning framework here. Okay, before introduce it, let's check a new video MLM we propose here, which is called the Motion Epic Fine-Grained Spatial Temporal Grounded Video MLM. So with Motion Epic, or reasoning framework can work. Motion Epic takes as input three sources, like text prompt, video, and spatial temporal scene graph representation of video. We employ the Vicuna as the backbone LM, and to perceive video input, we adopt the VIT encoder, Q-former projector, and also an STSG encoder to perceive STSG representation. Okay, by definition, an STSG consists of a sequence of single scene graphs corresponding to all video frames, with each scene graph comprising triplets in the video framework, like subject, predicate, object, where the subject and the object refers to the to visual proposals that are connected with the predicate relationship. And the rationale we integrate STSG representations are: first, STSG depicts the underlying core semantics representation of the videos, which means STSG is an ideal representation that we can use for video reasoning. And second, STSG is a type of fine-grained structural feature that can help effectively model the compositional spatial temporal semantics of the video. To enable a Motion Epic with the fine-grained pixel level spatial temporal grounding between videos and STSGs, here we investigate various distinct video STSG training objects for the MLM fine-tuning. So STSG annotations are used during the grounding or well tuning, and in the subsequent stage, the system is learned to automatically parse STSG, and thus supports STSG-free inference and reasoning for the downstream tasks. Here now let's check the VOT reasoning framework. So the overall idea is VLT divides the raw problem into much smaller and finer grained sub-problems that are easier to be handled. Here is the overall process. We consider an exact paradigm of a task decomposition, which contains 5 chain steps following a process from lower level perceptive pixel grounding to high level cognitive semantic comprehension. So step 1, task definition and target identification. So first, motion epic is fed with the raw video along with the text prompt of the video definition, format, and the raw question. As an initial step, we expect to identify the targets within the video that requires analysis, which is a crucial prerequisite for the subsequent in-depth reasoning. Step 2, object tracking. Here, we further ground the objective for spatial temporal character, like to track the target's trajectory. We leverage the fine-grained SCSG for the temporal grounding rather than directly tracking the original video frame. Step 3, action analyze. VLT further analyze the corresponding actions and behaviors by integrating the target's tracking in SCSG. For an accurate understanding of the target object motion, just observing the target itself is not enough. This should also refer the high-order neighbor nodes within the SCSG representation. Also, we further prompt the model to consider more potentially relevant common sense knowledge, which allows the model to connect the video pixel observations with the factual world, achieving a more in-depth understanding of the video. Step 4, question answering via ranking. So with the in-depth understanding of the target actions at hand, we can now answer the original question. We consider the multi-choice QA format, where the multiple candidate answers are provided, inspired by the human patterns of answering multi-choice questions. We also consider a ranking mechanism to determine the final answer. Final step, answer verification. Given that the complex video task often involves intricate questions and answers, and the entire reasoning process comprises lengthy chain steps, right? Multiple steps. It's essential to verify the answer provided in the previous step. So our basic idea is assuming that the question A, the answer A is correct. We evaluate whether the answer result is in contradictions with the input questions and the video in 2 aspects. First, checking the pixel grounding and the information if it lies with the facts presented in the video. On the other hand, prompt the model again from a cognition perspective to determine if the common sense implication inherent in the answer contradict any of the main observation inferred in the third reasoning step. If any consistency are found in perception and the cognition perspectives, we let it execute the fourth step. Okay, here we check the experiment part. Here are some basic settings. So we mainly focus on the complex types of video QA benchmarks. Overall, our motion epic under the VLT reasoning framework has boosted all the SOTA baselines by quite clean margins consistently. Here are the results on 4 benchmark dataset. Here are the results on the causal read QA dataset. Here are the results on next QA dataset. Let's check it in detail a little bit. First, by observing the video lava with and without COT prompting, we see that the improvements from COT for video reasoning could be quite limited. Further, by comparing the video lava with and without STSG integration, we notice that the structural fine-grained STSG features play a positive role in understanding videos. Third, by comparing the video lava plus the STSG with our motion epic under the same COT it is clear that the implicit integration of the scene graph features is quite superior to the explicit integration. Lastly, observing the motion epic under COT and all proposed VLT, there are huge performance gaps in between consistently on all reasoning scenarios and tasks. So this indicates that the great potential for proposed video of source reasoning. Also, COT exhibit stronger improvements than the direct prompting methods under the zero-shot scenario. Yeah. To evaluate how well or emotion epic is capable of video grounding, here we perform the probing task. We see that the motion epic achieves very competitive performance on par with the SOTA parser, even with human level performance. This shows that the motion epic shows reliable capability in providing the video grounding information to support the subsequent in-depth video reasoning. We further study the impact of different grounding while tuning objectives, and we see that the different atoms comes with different impacts, indicating the importance of video SCSG grounding fine-tuning. Here we further analysis VLT. Here we show that the motion epic with the VLT reasoning framework achieves quite exceptional result, comparable even to human performance. We further summarize the error cases and analyze differences in the 6 most frequent category of errors. As seen here, motion epic with the VLT significantly reduces the error rate of video lava, especially in terms of action semantics and the common sense understanding. Finally, we here present the visualization of a case study to intuitively understand the superior of our system. So overall, the entire reasoning of our VLT greatly improves the accuracy at each step through problem decomposition, meanwhile ensuring an explainable process decision rationale. Here is another visualization and another one more. Because we don't have more time to go through them, please check our paper for more details. Thank you for your interest, and yeah, bye bye.